So this is our syllabus. So in our syllabus, unit number 3 is PLD architectures and applications. So if we see the topics, then they are design flow, CPLD architecture, features, specifications, applications. Again, FPGA architecture, features, specifications, applications. The simulation and synthesis tools, and FPGA synthesis and implementation. So as such, if we see, this topic is very simple. And from examination point of view, there are standard 5 to 6 questions which are asked in the exam since years. That is why we staff members do not spend a lot of time. Maximum 2 lectures we spend for covering the whole unit. In that also, if we see, there is a uniform flow. CPLD, architecture, features, specification, applications. FPGA, architecture, features, specification, applications. As far as design flow is concerned, it is standard. So when we say PLD design flow, it means prototyping the PLD. That is how to convert a programmable logic device into the proposed digital system. That is what it means. And there is no point discussing design flow because you are actually doing it all these months in our part A assignments. So design flow for a programmable logic device is nothing but what we are doing in part A. That is writing the main model using VHDL language, synthesizing it, seeing the RTL schematic, seeing the technology schematic. After that, writing the test bench model, simulating it, and through waveforms, checking if the functionality has been achieved as per the truth table or function table. And the third step is once the functionality has been verified, then you use a floor planning tool such as Plan Ahead. And after that, you do pin locking and then you download the bit file into an FPGA. That is nothing but design flow. So only if our college is going on in offline mode, you could have got a clear idea about the third part or the remaining 1/3 portion of what is called as PLD prototyping. So PLD prototyping or CPLD prototyping or FPGA prototyping is nothing but it is the process of programming the programmable logic device so that it starts acting as the proposed digital system, in the sense it can now accept digital inputs, that is ones and zeros, from the real world, and it can process those ones and zeros and give the desired output. That means FPGA prototyping means nothing but converting the PLD into an ALU, converting converting the PLD into ALU, or converting the ALU into USR, converting ALU into FIFO, or converting the FPGA into somebody who can actually display characters on the LCD display. Okay, so you understand FPGA prototyping means it is the process of converting the FPGA into the proposed digital system. Okay, fine. So and then the synthesis and simulation tools and FPGA synthesis and implementation. This is nothing but what we have been doing. So I have made standard notes for FPGA synthesis and implementation and simulation tools. Basically, today's lecture, in fact, I can complete whole CPLD and FPGA architecture because CPLD architecture, FPGA architecture, what we are going to study as a part of syllabus is nothing but it is the basic architecture. That is why we say architecture of generic CPLD, architecture of generic FPGA, because CPLDs and FPGAs were something which were devised almost in the year 1985. So it is almost 35 years that CPLDs and architectures are in market. And what we are studying as a part of unit number 3 of VLSADT is a very old architecture, but still, although it is old architecture, that architecture's core still remains, and many other things have been added in and around the basic architectures of CPL and FPGA. So their functionality has reached to great complexities and also great bandwidths and very high data transfer rates. Okay, that is the difference. So it is worth studying the architecture of generic CPLD and generic FPGA, because if you study that, then if you read the data sheets of the modern day FPGAs, then you will appreciate that yes, this is what is the core and this is what has been added. Okay, so this was the overview of the whole unit number 3. So it is a very easy unit and one lecture should be sufficient. Okay, there are standard things to be studied here. Okay. So PLD is not something which you are going to hear for the first time. You have heard this before, mostly in second year. So as we know that PLD stands for programmable logic device. Okay, logic device. Okay, second important fact is that PLDs are classified as follows. Some of them you already studied in second year and some of them you are going to study today. So we can have a broad classification of PLDs in this way. So we have SPLD, which stands for simple PLD, and here we have high density PLDs. SPLDs are classified into many types. PAL, PLA, and we have PROM. PROMs are of different types. We have ROM, we have EPROM, we have EEPROM. And you know that PAL has programmable AND array. It has fixed OR array. PLA has fixed AND array, programmable OR array. Okay. these guys, they have programmable AND array and programmable OR array. Okay, so one thing is for sure, that because PAL and are all a combination of AND and OR arrays, and we know that an AND gate can implement a product term, and OR array can sum all the term. That is why PAL, PLA and PROM can actually implement any Boolean function which is expressed as sum of products, right? So all three of them can implement Boolean function expressed in SOP form. Okay. Another important thing is that in second year you must have studied or you must have solved numericals, that given function f1 is equal to function of a comma b comma c equal to summation of m 0 comma 2 comma 4 comma 7, and you had numericals that implement the following function using PAL, PLA and PROM, and you had some fuses, so you used to put a cross against a product term and used to put a cross against a sum term. So you have done all these things, but if already those devices are available now in the market, there are PAL ICs, PLA ICs and PROM ICs also. But the problem is why there had to be some manufacturers who had to go for what is called as high density PLDs, because the problem is that as long as the summation of inputs and outputs of a system is less than or equal to 32, till that time you can use simple PLDs. When the summation of inputs and outputs exceed 32, at that time it becomes very cumbersome to implement that function using SPLDs. You have to go for high density PLDs. So the limitation of SPLDs is that SPLDs can be used to implement a digital system as long as summation of inputs and outputs is less than equal to 32. Okay, 32. Okay, so for anything greater than 32 you have to go for high density PLDs. Okay, so high density PLDs also have their own classification, which is like this. So there are two broad categories. One is called as CPLD, that is complex PLD, and second is FPGA. FPGA, which stands for field programmable gate array. Okay, so we have CPLD, complex PLD, and we have FPGA, field programmable gate array. Okay, okay. Please remember one thing, that both of them, all of them in fact, are all digital systems. Okay, so I'll make a note here that Okay. And as far as SPLDs are concerned, SPLDs, if you want to implement any system, then you have to implement based on truth table. Okay. So I can also write down a note here that, okay, implementation is based on burning fuses as per truth table. Okay. So if you have a truth table, you have the expression which is expressed in min terms or max terms, then you can burn certain fuses to implement it. But here in case of high density PLDs, you have to compulsorily use an HDL. Okay. So we can write a note here that, okay, implemented using HDL, hardware description language. Okay, so implementation is based on burning fuses as per truth table, and it is implemented using hardware description language, which can be VHDL, or it can be Verilog. Okay, any of this, fine. There is system Verilog, but then it is used more for system verification and not for prototyping. Okay, check. So now CPLDs again, there are many types. There are three types basically. We have basic CPLD, and we have advanced CPLD. Some numbers are from Xilinx company, XC95 series, and here we have Cool Runner series. Standard numbers are XCR 3064 XL VQ100. This is the big IC number. Okay, so we have XC95 series. Just like in voltage regulators, we have 78XX series positive regulators. We have 79XX series, that is negative voltage regulators. Similarly, we have XC95, which is called as basic CPLD series, and then advanced we have Cool Runner, and the IC number is XCR 3064 XL VQ100. Okay. Similarly, now if you go down, full programmable arrays, they are also classified as follows. So it is called as anti-fuse type, and we have SRAM based. Okay. Another classification which is given for FPGAs is also like this. We have fine grain and we have coarse grained also. FPGAs. Okay, so fine grained and we have coarse grained, we have anti-fuse, and we have SRAM based. Okay, right. And then as far as FPGAs are concerned, Here we have two vendors, Intel and we have Xilinx. Just like we have Intel and AMD for laptop and desktop processors, we have MediaTek and Qualcomm for mobile processors, smartphone processors. Similarly, there are two main vendors for manufacturing FPGAs, that is Intel and Xilinx. So Intel has its own family. Um, so Intel doesn't manufacture CPLDs anymore. It may be, anyways, I'll still write the numbers. So it was formerly Altera, so I can say it had Max 3000, Max 7000 series. That was the product. And as far as FPGAs are concerned, FPGAs, then they have Stratix family. Okay. Similarly, as far as Xilinx is concerned, FPGAs. So here, as I said, we have here we have Spartan, we have Vortex, Artix, Kintex. These are four FPGA families from Xilinx. Spartan, we have the following members: Spartan 2, Spartan 3, Spartan 6. Vertex, we have 2, 4, 5 and 7. Here we have only 7. Here we have only 7. Okay. Similarly, as far as these three are concerned, they also have three flavors. Conventional, ultra scale, ultra scale plus. Just like your Samsung Galaxy S20, S20 plus, you have Samsung Galaxy, S20 Ultra, something like this. So what is the difference between conventional, ultra scale plus? The difference lies in the smallest FinFET which is there. So conventionals are manufactured using 28 nanometer technology. Ultra scale are manufactured using 20 nanometer technology, and ultra scale plus using 60 nanometer technology. And this particular family, actually uses 3D MOSFETs, also known as FinFETs. Okay, also known as anyways, fine, heterogeneous technology. Okay, fine. So now we define PLD prototyping or CPLD prototyping or FPGA prototyping means converting a programmable device into a programmed device. Okay, using standard design flow comprising of synthesis, simulation, and downloading. Okay, fine. One important question which usually asked during Viva is FPGA and ASIC? So basically, although so many things are there, we are only interested in FPGAs because that is the device which we are going to use in the lab. Okay, the question is CPLD or FPGA an ASIC? So all of you know what is an ASIC. ASIC is an application specific integrated circuit. So if a question is asked, is CPLD or FPGA an ASIC? Now ASICs are of two types. Okay, so ASICs are of two types. One is called as semi-custom ASIC. A second is called as a full custom ASIC. Okay, so understand that CPLD comma FPGAs are an example of semi-custom ASIC, not a full custom ASIC. The reason is that a full custom ASIC, you can customize everything, right from the number of transistors to the propagation delay to the area which is occupied on the chip. In semi-custom ASIC, you have freedom, but not complete freedom. So in full custom ASIC, you have total control over propagation delay, power dissipation, and area. How much will be the area in micrometer square? How much will be the maximum power dissipation, or how much will be the minimum propagation delay? Okay, So there we have full control. But here the problem is that the architecture is standard. CPLD and FPGA is manufactured with a standard architecture by Intel or Xilinx. So you cannot change the architecture. Okay, so you have to accept the architecture of the PLD. You have to accept the technical limitations of the PLD, and then you have to implement the functionality. Okay, so FPGA and CPLD are called as semi-custom ASICs because why? The reason is this. The reason is this, that although they are reprogrammable. Why reprogrammable? Because you change the main model, the functionality changes. So although they are reprogrammable, you must accept the technical limitations of the device and thereby realize your desired functionality in them. That is why they are called as semi-custom ASICs. Okay, so they have limited freedom. Semi-custom ASIC. Okay, so here we can say that you have full freedom. Fine. Okay. So the briefing. Now we go to CPLD. CPLD architecture. Okay. Now, one point I would like to make here, that since CPLD has limited applications, Xilinx has stopped innovating and promoting CPLDs. As far as basic architecture is concerned, it looks like this. Yeah. So what is in front of us is called as architecture of a generic CPLD, and it is very, very simple. So we see here that there are four blocks called as PLD blocks. So PLD blocks basically is called as programmable logic device. Basically, more specifically, it is a PAL-like block. So many manufacturers, when they release their architecture for the CPLD, they actually say that this is a PAL-like block. So whether you write a PAL-like block or PLD, it's same. So what do you mean a PAL? As we said that what is a PAL? PAL is a programmable logic device in which there are two arrays, AND array and OR array. AND array is programmable and OR array is fixed. So this is called as PAL-like block. That means what? A CPLD within itself, one of the building blocks is a PAL. So there are four PAL-like blocks. Now we see here how it is connected. So for every PLD block, there is one IO block. So there is this PLD block, IO block, this PLD block, IO block, this PLD block, IO block, and this PLD block. So if there are four PLD blocks, there are four IO blocks. Basically, it is an input-output interface. So if we see how the arrows are connected, all arrows are bidirectional. You see here, there is not even a single arrow which is unidirectional. That means what? Data flows in both the directions. Now see here, there is something called as an interconnection matrix in between. So interconnection matrix in between, what it does, it establishes a communication between different PLDs. That means if the bottom left PLD wants to communicate with the top left PLD, then what it will do, it will send information through the interconnection matrix. So interconnection matrix is connected simultaneously to all four PLD blocks, and whenever any signal enters into the CPLD for being processed, it is always passing through IO block. So IO block is nothing but input output interface. It performs all important functions which an IO interface usually performs, that is bringing about electrical compatibility between the peripheral and the logic blocks, bringing about compatibility between the data formats with the peripheral understands and the CPLD understands, also bringing about compatibility between operating frequency differences and data transfer rate differences. All these incompatibilities on electrical data frequency level are all taken care by IO interface. So all signals coming inside the CPLD for processing will always pass through IO block and then it will enter into the logic blocks. Similarly, whatever processing is done by the CPLD, the signals will again pass to the IO block and go to real world. So signals coming from the real world and going into the real world always pass through IO blocks, right? So CPLD's basic architecture consists of multiple PLD blocks or PAL-like blocks. Every PLD block has an IO block dedicated to itself, and all the PLD blocks are connected to each other through what is called as an interconnection matrix. Now the complexity lies here. So IO block is okay, PLD block is okay. Now what does the PLD block contain? So PLD block consists of three things. I repeat that now we can summarize here that every CPLD, it consists of multiple PLD blocks. Every PLD block contains three things. One is macro cell, one is multiplexer, and a D flip-flop. When I flash, you will come to know. Okay, so we can actually write down here that any CPLD, whether it is basic or advanced, I can say so we can make statements here. CPLD is a combination of multiple PLD blocks. Okay, this is first statement. Now I am going to show you another diagram. That diagram actually shows what does every PLD block contain. Okay, again we insert another diagram. Yeah. So the next figure which is there in front of us is called as a PLD macro cell. It indicates that every PLD contains not one macro cell, multiple macro cells. Okay. Now you see here, as I told you that every macro cell contains PAL-like logic. You see here, there is AND gate and there is OR gate. So this AND gate represents AND array and the OR gate represents OR array. So when you have a combination of AND gate and an OR gate and a NOT gate, basically it is nothing but a multiplexer. It is AND or NOT logic. So it has PAL-like logic, it has multiplexer here, and it has a D flip-flop here. That is why I told you that every macro cell is a combination of PAL-like logic, multiplexer, and D flip-flop. So I will again write it here. Okay. So I'll write here another statement. Each PLD block contains multiple macro cells as shown above. Okay. So each PLD block contains multiple macro cells. Okay. Now, as indicated above, each macro cell now consists of the following things. Okay. So now I can tell PAL-like logic. Second is MUX. Third is D flip-flop. Okay, so we can write it like this now. It's very clear, it's a D flip-flop. Okay, so we have put the equations now. Every CPLD is a combination of multiple PLD blocks. Each PLD block contains multiple macro cells, and each macro cell in turn consists of PAL-like logic, multiplexer, and D flip-flop. Now let us put some statistics. Now I will write down some sample numbers from Xilinx. Okay, justify now. Okay, consider the basic CPLD from Xilinx Incorporation. Okay, so number is XC9572. Okay, let us now understand what does it mean. Okay, so the first field is XC, which as usual stands for Xilinx Corporation. Second is 95 and third is 72. And then third, what is there is called as PC 84. So we have many fields here, PC, and we have 84. Okay, so this is Xilinx Corporation. This indicates it is basic CPLD. Yeah, this is important. This 72 indicates that a device contains 72 macro cells. This is the package, plastic leaded chip carrier, and this is the number of pins. Okay. Similarly, there is another device of the same family which indicate this number is XC95108. Then we have 256. We have 512. So what these numbers indicate that this device contains 108 macro cells, 256 macro cells, and 512 macros. So it indicates 108 macro cells, 256 macro cells, and 512 macros. Okay, so in essence, Xilinx expresses the logic density or ability or complexity of its CPLD by in terms of macro. So you can say that macro cells, we can say that number of macro cells is the unit used to express the logic density of CPLD. So this is very important. The number of macro cells is the unit used to express logic density of CPLD. Okay, very, very important. Okay, now so we see here a similar diagram is there, as I have told you that. Okay, so we can say here these two are same. Exactly the same. Okay, as I purposefully put because I had used the word PAL-like block on our PLD. That is why. So both of them are same. So in the exam, when it is asked to draw the architecture of generic CPLD, you can either draw this diagram or you can draw this diagram. So no issues at all. Okay. Yeah. So as I said, specifications usually. So if you want to say specifications, I can actually flash some data sheets for you. Okay, rather than this, actually I'll open XE9572. Yeah. So this is XE9572, that is the basic CPLD from Xilinx, and we can see here what are the specifications given. So pin to pin delays are 7.5 nanoseconds, 72 macro cells. I told you this thing, 72 macro cells with 1600 usable gates, up to 72 user IO pins. Imagine, okay. 5 volt in system programmability. So it is basically an old device. So it is running on 5 volt system, which is too old. So 90 product terms are there, 18 macro cells within function block. It is complying to JTAG standard, IEEE standard 1149.1. So it has 24 milliampere outputs. So these are the buffers which are there inside. Output buffers are there. It is using advanced CMOS fast flash technology, CMOS logic family. Here that's there. So CMOS was used even before 35 years. Okay, so it is available in many packages. 84 pin, which I told you, XC95722, PC84. As I told you, PC stands for PLCC, plastic leaded chip carrier, 84 pin, 100 pin TQFP. That's it. Okay, so all different graphs are given. ICC stands for quiescent current that is drawn from the supply. You can see that. Okay. So these are some electrical ratings. So we have two voltages, VCC INT and VCC IO. So VCC INT is called as core voltage. That is the voltage which drives the logic blocks inside. So because logic blocks, they operate at a higher frequency, they are driven by a lower voltage. VCC IO is the IO voltage, that is the peripherals. And there are some noise margin levels here. Okay. And as I told you, this is the pin information. As I told you, 95 is device type, -7 is speed, PQ100 is there, temperature range. So many things. If you read the data, you will come to know all these things. Let us see if we have something in Cool Runner. So I told you Max 7000. So Max 7000 was a CPLD from the competitor Altera. I had written here, if you remember. I had written here Max 7000 from Intel Altera. Okay, Max 7000 I had written. That is what I was speaking about. We have Cool Runner 2. Okay, so these are Cool Runner 2 means actually it was manufactured for low power dissipation. So the name is Cool Runner. Okay, ultra low power, high performance. Okay. So Cool Runner 2 is also called XPLA, extended PL it is called. Okay, you see here higher densities 256 macro cells, CMOS CPLD. It is manufactured using 180 nanometer technology at that time. So here so these are sample numbers and some other devices which are available are speed gate is -10 here. Xilinx Cool Runner 3064 some technical specification. VQ is the package. 100 is number of pins. Okay, so this is from Xilinx. Okay, fine, already written it. And this is also from Xilinx. And we have from Altera. Altera is now Intel. There was a merger. Okay. CPLDs, both of them are CPLDs. Okay. So as far as applications are concerned, fine. About applications, we can discuss tomorrow. No problem. Okay. So tomorrow we will cover elimination of hazards, and we will jot down applications of CPLD, and then we will start with the second and the only unit left, that is FPGA's basic architecture, specifications, applications, and sample devices. And also then we will have contrasting FPGA versus CPLD. Okay. Yeah, that's it. Anybody has any questions, they can ask.